So thank you. Once a year, we have a lecture we call the PH lecture in honor of Paul Hurtelendy. Paul Hurtelendy was a member of the Smithsonian's National Board for an extended period of time, and he took an interest in our work. And it's to this date, I still don't quite understand how he came to this, because his career was as the music and drama critic for the San Jose Mercury News. But nevertheless, he was very interested in supporting the careers of brilliant young people, and he asked us to, with his support, to have an annual lecture to be called the PH lecture, to be given to a young scientist at the Center for Astrophysics. And deliberately, what young meant was left kind of vague, so we have a lot of discretion. It also means that we have a lot of really very interesting people to choose from. And this year, we have an extraordinary example about to speak with us. Laura Kreidberg is our speaker. She's a junior fellow at the Harvard Society of Fellows. And prior to coming to Cambridge, she was at the University of Chicago in grad school, and before that at Yale. So quite a pedigree. Her research focuses on mapping the climate, chemical composition, and ultimately the habitability of worlds beyond the solar system. A noble goal that many of us subscribe to. So what I'd like to do now is actually just make a brief presentation of the certificate to you, right? Yeah, shake your hands, right? Picture taking, right. Okay? Now, I'll take this. You'll get it back.
Okay.
The floor is yours, right?
Thank you. All right, am I on?
You're on.
Okay, can everybody hear me? All right, good. Well, first I wanted to just say thank you so much. It's really an honor to be able to speak here, especially in this context. I have to say I'm continuously, just amazed and impressed by all of the young people here at the CFA that make it such a stimulating place to work, and so I'm doubly honored to have been chosen to give this talk. All right, so as Charles said, I'll be talking today about my work on exoplanet atmosphere characterization. And I want to start off with a tweet, actually. This is a quote from Jill Tarter about a year ago at a WASP meeting, and she said, "We can now say with statistical certainty that there are more planets than stars in the galaxy." And I like this because I feel like it gives you a sense of scale of how important a part of the galaxy and the universe planets are, and it's only been in the last few decades that we've even begun to probe the existence of planets outside of our solar system, but the field has taken off enormously since then. And we have discovered a huge variety of planetary systems. 20 years ago, we didn't know whether there were other planets at all, let alone whether they looked like the planets in our solar system. And so here's a figure showing planets color-coded by detection method as a function of orbital distance from their host star, with planet mass on the y-axis. And the solar system planets are marked with black here. And these are just detections, so this isn't representative of the population per se. Bigger planets are easier to detect, so there's a lot of selection effects here. But you can get a feel for the diversity of planetary systems that are out there, and immediately you see that there are planets with much shorter orbital periods than are seen in the solar system. Mercury is off the bottom of this plot here because it's a low-mass planet. But many of these planets have orbits interior to that of Mercury. There are planets that are the size of Jupiter with orbital periods less than a day, something that was never imagined before extrasolar planets first started being detected. And in many ways, I think this plot raises more questions than it answers, because it shows us that nature produces a huge variety of planetary systems that often look nothing like our own. And so we're left with many questions about how these things form, how they evolve, and whether any of them are producing planets at all like our own. So the focus of my work is on exoplanet atmospheres. And I don't want to diminish in any way the huge number of things we can learn from studying the orbital architecture, the mass and radius statistics of planets. But what I will say is that if you add the atmosphere as an additional axis along which to characterize your planet, you can learn a huge amount about it. And so in the case of a giant planet, the atmosphere, the primordial atmosphere, is accreted from the protoplanetary disk as the planet is forming. And so it provides a fossil record for the formation conditions as the planet swept up gas and dust from the nebula. In the case of a small planet, the atmosphere is a record of the evolutionary history. It's thought that small planets can't retain an original, a primordial hydrogen and helium envelope, but they can outgas material through volcanism. They can get at later stages ices delivered by comets. And it's unknown a priori exactly how these processes play out. We only have a small number of terrestrial planets in our solar system, and you can see from our friends here, Earth, Venus, and Mars, that there's diversity even within one system. And of course, if we ever want to address the question of whether other planets are inhabited, we'll have to look at their atmospheres to see whether their climates and compositions are hospitable for other living things. Okay, so I want to give a just very brief overview of how we actually go about characterizing the atmospheres of exoplanets. I remember as a beginning graduate student, I heard that people were trying to do this, and I thought, man, like surely that's not possible. And then I went off and did my thesis on it and convinced myself otherwise. So one technique that we use is called transmission spectroscopy. And the idea here is that when a planet transits in front of its host star, a small fraction of the stellar flux can filter through the atmosphere. And so I have a cartoon illustrating this here with the planet cores, the black circle in the middle, and then the surrounding annulus represents the atmosphere. And depending on what wavelength you look at, the atmosphere can have varying opacity. And so this shows up if you measure the size of the planet as a function of wavelength. That's the so-called transmission spectrum. You can use that to work backwards and figure out what molecules are present in the atmosphere doing the absorption. And on the right here, I'm just showing some simple scaling relations to give you a feel for what physical parameters go into setting the size of these features. It has to do, of course, with the size of the planet relative to the star, but also with this parameter h, the atmospheric scale height, which is, if you remember from hydrostatic equilibrium, the length scale over which the pressure drops by a factor of E. And that depends on the temperature, the mean molecular weight, and the surface gravity. So for the very best case scenario, so the easiest case to detect, that would be a hot Jupiter with a predominantly hydrogen and helium atmosphere, the amplitude of these features is going to be about 0.1% at best. So this is a very, very challenging measurement to make. Okay. So the corollary to the transmission spectroscopy technique is emission spectroscopy. And I have a cartoon for this as well. I should say these cartoons are available on my GitHub account. I get requests for these a lot, so if you are interested in using them, you're very welcome to download them. All right, so the way emission spectroscopy works is that so for a tidally locked planet, it's expected to have a hot, continuously irradiated day side and a much colder night side. And as the planet completes an orbit around the star, we see different viewing geometries. And so here we have the planet transiting, and then as it comes back around, the day side rotates into view, and so we get an increase in brightness. These systems are too far away to spatially resolve the planet from the star, and so we're forced to rely on combined measurements of the star and the planet together. And then we see the day side rotating back out of view. So similarly to the case for transmission spectroscopy, the biggest amplitude signal you would possibly expect is about 0.1%. Hotter planets are easier. The larger the planet is relative to the star, the easier you're doing. But 0.1% is the best case scenario. Okay. So, the title of this slide, this is a watershed moment for exoplanet atmospheres. I didn't want this to be my title because I feel like it's sort of a an overly cliched kind of hyperbole that you would put in an observing proposal. But I really believe that it's like actually true, and so I decided to keep it in there. And there are two reasons that I think now is such an important moment for exoplanet atmospheres. One of them is that we have now discovered many, many transiting planets around bright nearby stars with the promise of hundreds more soon to come from the TESS mission, which is scheduled to launch in just over a month now. And so we'll have, for the first time, the targets we need. TESS will be looking at the brightest stars in the sky, searching for transiting planets on short period orbits, which are ideal candidates for atmospheric studies. And many of these are going to be small planets, so Neptune, all the way down to Earth-sized planets. And so this adds to the heroic efforts that have already been going on from the ground to detect these tiny, tiny signals. And we will be set up perfectly with all of the targets that we want to do this atmospheric characterization work. All right. The second reason I think this is a watershed moment for exoplanet atmospheres is that JWST is going to launch real soon. And I like to say that JWST is 10,000 times better than any other facility available currently for atmospheric characterization. Hubble is the state-of-the-art facility now, but the things that James Webb will add are factor of 10 improvement in collecting area, factor of 10 bigger wavelength coverage, so it'll extend all the way out to 30 microns, enabling us to look at the atmospheres of much cooler objects than have previously been accessible. It also gives about a factor of 10 improvement in spectral resolution, so we can really start to resolve the shapes of spectral features and learn about the atmospheres in more detail that way. And finally, the pointing stability. This might seem like a detail, but these measurements are so difficult that where your spectrum is on the detector at the pixel by pixel level turns out to be very important for being able to make the measurement at all. And so this factor of 10 improvement in stability is going to be a huge advantage in atmospheric characterization. Okay, so the way I decided to set up my talk is split up by planet size. So I'm going to start first talking about big planets, planets like Jupiter, move on to medium-sized planets, and I'll define what those are when I get to them. And I'll finish up talking about small planets more like our own. And I'll be covering the work that's currently being done with Hubble and Spitzer, as well as the kind of constraints we expect to make with James Webb. Okay, so first, some questions for big planets. They're very basic, just to start. We want to know what their atmospheres are made out of, what atoms are present there, what molecules, what are the abundances of those species, and what are the abundance ratios. Those are set by the conditions in which the planet formed. So as the planet is accreting gas, the composition will be related to the surface density of solids, the size and composition of planetesimals, the relative accretion rates of gas versus ices. And so we can hope to measure the composition now and learn all of these details about the planet formation process that are not accessible in other ways. We also want to know generally, what are their climates like now? You can take a planet the size of Jupiter and put it on a 1 or 2 day orbital period. It's being blasted by stellar radiation on one side. What does that do to the wind, the circulation patterns in the atmosphere? This is a much different regime of atmospheric physics than we would ever study in the solar system. And finally, do other planets have clouds? Are there clouds or hazes in their atmosphere, and what are those made out of? So our basic expectations for the composition of a giant planet is that it's mostly hydrogen and helium with trace amounts of other species. Water is an important one because it's the dominant component by mass of icy planetesimals, and so it provides a tracer for what kinds of planetesimals are being accreted. It also has very high opacity, and so it's easy to observe, which is convenient. Turns out we actually don't know the water abundance for Jupiter very well, because Jupiter is so cold that the water has mostly condensed out of the observable part of the atmosphere. And so even though the the Galileo probe entered the atmosphere, we still don't think we know the water abundance very well because the Galileo probe landed in a dry spot. So I think it's possible to make constraints, to make estimates of the water abundance for gas giant planets in extrasolar planetary systems, perhaps better than it's possible for Jupiter. And so this has indeed been borne out. So these are measurements from the Wide Field Camera 3 on Hubble from about 5 years ago now. And these were revolutionary measurements. They made use of a new observing mode. Hubble was, turns out, not designed to look at bright nearby stars. It was designed to look at faint, distant galaxies for some reason or other. And so often, if you're looking at a bright target, you'll saturate the detector in the shortest possible exposure time. And so this was a real challenge for observing nearby planetary systems. And so the folks at Space Telescope devised a new observing mode where you scan the spectrum along the detector in the spatial direction over the course of an exposure. And that allows you to both average over the qualities of many different pixels, so you're less sensitive to sensitivity variations between them, and you can make an efficient observation and collect a lot of photons. So that was a big technical breakthrough and resulted in these beautiful spectra that showed that, just as we expected, there are big water features in the near infrared. And so what I wanted to do as a grad student is take a step beyond this and say, okay, we see that indeed the water is there, but the second question is, how much water is there? What is the water abundance? And so I pursued very high precision transmission and emission spectra measurements for a hot Jupiter called WASP 43b. We observed a total of 6 eclipses and 5 transits of this planet. And the spectra I'm showing on the left here. So it's the emission spectrum on the top. You see a very nice absorption feature due to water. The transmission spectrum on the bottom, and again, absorption is up in transmission spectroscopy, so that also corresponds to a water absorption feature. And together with Mike Wine, we did a retrieval analysis where we varied the atmospheric properties, so the climate and the composition, to see what kinds of scenarios could reproduce the data. And we got a very tight constraint on the water abundance from about 1/2 to 3.5 times solar. And I should clarify that if you, talking about solar abundance of water, we know that the sun is too hot to have water, but if you take a solar composition gas and you put it at the temperatures and pressures in the photosphere of the planet, that's the measurement we're talking about. So this was at the time the most precise measurement of water abundance for a planet outside of the solar system. And we decided to use it to start comparing to the atmospheric metallicity of the known solar system planets. And this is what it looks like. So there's a well-known trend that the lower the mass of your planet, the more metal-enriched the atmosphere is. And we think that's because as the planets are forming, if there's less hydrogen and helium there, you have some icy planetesimal fall in, you get relatively more pollution than you would if you have a much more massive hydrogen-helium envelope. And so it's really exciting for us to see that WASP 43b falls beautifully along this solar system trend. And I'll say, I'm not claiming that we have solved the mysteries of planet formation by making this single measurement. The reason I'm excited about it is that it's a proof of concept that it's possible to start making precise abundance measurements for planets that are hundreds of parsecs away. And even if we never get the same precision constraints that are possible from in situ measurements in the solar system, the advantage of exoplanets is that we could do this for 1,000 and see how this trend holds up over a larger mass range than is available to us nearby. So, just as a preview, this is what we expect this kind of measurement to be like for JWST. So these are planned observations from the recently accepted early release science program. I'm a part of this. This is science that is to be carried out during cycle 1. The data will be made publicly available immediately so that folks can learn how the instruments work and figure out the best observing strategies for future cycles. This particular ERS program is the largest of all the programs that were accepted. It's about 100-person collaboration, which is definitely the biggest group I've ever been part of. And let me tell you, I learned a lot about people and how they work together, or not, as the case may be. But we did it. We did it. And it's an 80-hour program that includes transit observations of a hot Jupiter to be determined since the launch date has slipped. We're working on identifying the best target for the new launch window. But we expect to make similar kinds of constraints on whatever target we end up observing. And so here is a comparison of the constraints on metallicity and carbon to oxygen ratio that we could get based on existing Hubble data that I'm showing in yellow there. So that's the blue histogram compared to the combined inference based on all of the JWST data that we expect to collect for this program, and that's shown in red. So you can see that the precision of the constraints improves by more than an order of magnitude, which is really, really exciting. And I'll add to that these JWST measurements are going to be amazing, but I don't expect to get enough JWST time to be able to do this 1,000 times over. And so I'm on the science team for Finesse, which is a dedicated atmosphere characterization mission that has been proposed. And the idea behind this mission is that it would obtain transmission, emission spectroscopy, and phase curves for a sample of 500 to 1,000 exoplanets that will be discovered by TESS to start to do this in a statistical way. So measure atmospheric composition, metallicity, as a function of planet mass, and compare that to planet population synthesis models to start to learn about these bodies as a whole population and work backwards from that to infer how they formed. And so both of these, so Finesse is the American side, Ariel is the European side, and both of these have been selected to move forward in the proposal process. And we're waiting to hear about what ESA decides to do before the future of Finesse is decided. Okay, I want to change gears a little bit, and so I feel like I've presented the ways in which planets are these simple, idealized probes of how the planet formation process works, but they're more complicated than I've let on, and I want to talk about that a little bit now. So I'm saying here planets are round. You guys all know this. Yes. See, all right. Some of you are awake. Some people are shaking their heads. All right. So planets are round. And what that means is that, especially if you're just irradiating a round thing on one side, and it's orbiting, it's rotating, that you would not expect a perfect homogeneous climate and composition on such a body. And so I got really interested in how well we can study the climate, whether we expect significant variations from day side to night side, and whether those are measurable. And so I want to show some results from a paper I just submitted a couple weeks ago, where we observed a phase curve of another hot Jupiter. This is the planet WASP 103b. This is a very, very, very short period planet. It goes all the way around the star in less than 24 hours. And which makes it a great target for phase curve observations because you don't have to ask for that much telescope time. So we observed this thing with Hubble Wide Field Camera 3 that gives us spectroscopy from between 1 and 2 microns, as well as with Spitzer photometry at 3.6 and 4.5 microns. And just to convince you that this is hard, here's the before and after shot. This is with all the systematics included on the left. That's how the raw data come out of the telescope. And then if you spend 5 years getting a PhD, you can turn this into that. And it comes out really nice, just like the cartoon I showed at the beginning, which is continually amazing to me that this actually works. And so just a few things, you can see that, so here's the secondary eclipse in the middle here. And so that represents when the planet is behind the star, so that's the baseline stellar flux alone. And any additional flux that you're seeing is due to the planet. You can see that there's a big contrast between the flux on the day side, that's phase 0.5, versus the flux on the night side. So this thing is very, very hot on the day side, very, very cold on the night side, fairly symmetric on either side of secondary eclipse. But we wanted to take this and work backwards and figure out what kind of climate on the planet could produce phase curves like this. So with a graduate student, I developed a Python package called Spiderman. And the thing that this package can do is take any brightness distribution for the surface of the planet. So you take temperature as a function of latitude and longitude and produce the corresponding phase curve. This turns out to be computationally very annoying, and Tom did a great job figuring out a clever algorithm to calculate it precisely and quickly. So here is the result of one model. We wanted to first take all the physics out and say, suppose that you're just fitting some spherical harmonics temperature map to see if you can reproduce the phase curve. And you can do a pretty good job. So this is the spherical harmonics fit on the left. And on the right is the corresponding temperature map that comes from there. You can see the day side is really, really hot, hotter than 3,000 Kelvin at the substellar point. That's 0, 0. And the temperature drops by 1,500 degrees on the night side. Now, it's unclear to me how physical this is. We wouldn't necessarily expect the poles to be higher temperature than the equator, but it does reproduce the data fairly well. We also fit another map that was more physically motivated. This is a kinematic model that predicts analytically the temperature distribution you would get if you take a parcel of gas, heat it up, and let it advect around the planet with some constant wind speed. And you can see that this also fits the data pretty well, but it's pretty different as a temperature map from the spherical harmonics model. The night side temperature is constant. The substellar point has a sharper gradient from the latitude, longitude 0, 0 to the terminator. And the peak temperature is higher. It's close to 4,000 Kelvin. And so it's hard to tell with this color scale, but it's more than a 500 Kelvin difference at the substellar point. So that's interesting in and of itself, that there are multiple models that have very different temperature maps that can still reproduce the data. Even more dramatically, we can fit a really simple model that just has two temperatures, so a day-side temperature and a night-side temperature. And that also fits the data pretty well. So I'm still working out for myself what I want to take away from this, because we're starting to see that some models are favored over others. You can see that the two temperature model doesn't fit as well as the spherical harmonics model, but I think that this is the kind of question that we're going to have to start grappling with as we try to understand the 3D structure of these objects, because if you're looking only at a hemisphere average of your temperature map, it's mathematically totally, there are many possible maps that are degenerate with each other that could reproduce the same phase curve shape. So I think this is a case where we're going to have to partner closely with theorists who are predicting the 3D temperature structure to try to interpret what the true climate is. And indeed, that's what we did here. So this is a GCM, a 3D global climate model from Vivienne Parmentier, that I'm showing in the dashed gray line. And you can see that it fits the data pretty well. And it's also most similar to the spherical harmonics temperature map. So this is new. This is the first time that maps of this variety have been fit to a phase curve. In the past, it was only a simple sinusoid that was fit. And so I think that this is an important step forward in trying to figure out as much detail as we can about the climate of these planets based on phase curves. Okay, so now given this climate model that we have some insight into what the temperature of the photosphere is, I realized that the planet is close in temperature actually to a lot of stars. So the day side on the bottom here is about 3,000 Kelvin, night side is closer to 2,000 Kelvin. So I said, oh man, we have spectra at these different phases. What do they look like if you compare them to a star, a free-floating object of similar temperature? So these are brown dwarf spectra on the right, and the dashed lines represent black body fits. And you can see right away that these things are not the same. So the data for WASP 103b, the planet, are all consistent with a black body, whereas the stars have very noticeable absorption features due to water at 1.4 microns. And this is weird because normally, in astronomy, the temperature is a fairly good proxy for the qualities of an object. And so the question for us is why does this planet look so different from a star of the same temperature? And what we figured out by running 3D models is that for the planet, we actually expect water to dissociate on the day side of the planet. And that's not true for the stars because the surface gravity is so different. And so the surface gravity will set the pressure of the photosphere, and at deeper pressures, it's easier for water to stay together. And so because the planet has so much lower surface gravity, the water dissociates pretty easily. And so these are maps showing the predicted abundances of CO, H2O, and H-. And you can see that the H2O in the middle drops by about an order of magnitude from the night side to the day side. And that is sufficient to explain the absence of water features that we see in the spectra. But on the other hand, CO, which I'm showing in the second row there, is expected to stay basically the same abundance all the way around. And so the question we asked is whether we can see the CO or not. And it turns out that we can. So here, this is just the day-side spectrum from phase 0.5. And the Hubble data is shown on the left, but we also have Spitzer measurements. And you can see at 4.5 microns, the planet-to-star flux ratio is very discrepant from what you would expect from the best fit black body I showed before. And that corresponds very closely to a spectral feature from CO. And the reason we're seeing it in emission rather than absorption, we think, is that the planet's day side has a thermal inversion. So it gets hotter as you go up in the atmosphere rather than cooling off. This is something that's been proposed for hot Jupiters before. And it could be due to having some high altitude absorber that absorbs a lot of optical light. So titanium oxide is the classic example. There's a reason it's good sunscreen, right? It absorbs high energy radiation. And so if you have TiO high up in your atmosphere, on the day side, it can heat up those upper layers, and you see features like this in emission rather than in absorption. This is similar actually to why we have a stratosphere on the Earth. In Earth's case, there's ozone in the upper atmosphere that, thankfully for us, absorbs UV light and heats up those upper layers. And so we're seeing a very similar phenomenon on this much, much hotter planet. And another thing we can see here is that same emission feature doesn't show up as an emission feature at all phases of the planet. So here's phase resolved spectra, where 0 is corresponding to the transit when the planet is directly in front of the star. 0.5 is the eclipse when the planet is behind the star. And you can see, let's see if this is going to work. Yeah, so you can see that on the night side, that same feature is seen in absorption rather than emission as it is on the day side. And so what we're starting to see here, I think, is changes in this thermal structure with longitude on the planet. And that's exactly what you would expect, because if you remove your heat source, if you're not looking at longitudes where the stellar flux is hitting the planet, there's no mechanism to create a thermal inversion. And so we're starting to see the effects of that in the data that we have. So all of this is to say that planets are round, and that this turns out to matter in terms of the composition and how that changes with longitude on the planet, and also the thermal structure. And so I think that it should serve as a reminder to us that when we observe planets, when we don't have phase curve observations, but rather we're getting isolated snapshots, either from the transmission spectrum or the emission spectrum, that there's a lot of complicated phenomena at play, and those should be included in our models when we're trying to infer the atmospheric properties of the planet. So I'm really excited that also as part of this early release science program, a phase curve observation is included. I'm co-chairing the working group that planned this observation. So we're planning on getting a phase curve of WASP 43b with MIRI LRS, which provides spectroscopy between 5 and 12 microns. And the really neat thing about this is that at those wavelengths, we'll be most sensitive to the composition of the planet on its night side. And there's all kinds of action we expect on the night side. The temperature drop is so dramatic that we expect clouds to begin condensing. Some of those clouds might advect around to the day side and influence the kinds of measurements we make during secondary eclipse. And so by using these long wavelengths to characterize the night side of the planet, we'll get an unprecedented view into the chemistry and physics that are going on there. Okay. I want to change gears here before I use up all my time on big planets and talk about medium planets a little bit. So here are some questions that we'd like to answer for these planets. They're very familiar. I think they're almost exactly the same as the questions I listed for giant planets. We want to know what they're made out of, what their climates are like, do they have clouds or not. But for these slightly smaller planets, we're also interested in why they are not Jupiters. If you take something that is like 30 Earth masses, why wasn't it massive enough to experience runaway gas accretion and turn into a Jupiter? These planets are very abundant. So these are planet occurrence measurements from a paper by B.J. Fulton showing the occurrence rate of planets. And these are just planets with periods less than 100 days as a function of planet radius. And you can see that there's a peak here for terrestrial planets and a peak here at about 2 to 3 Earth radii. This is weird. Our solar system does not have a planet of this size. Uranus and Neptune are down here. And then there's a gap from there to terrestrial planets. And so these things, which appear to be among the most abundant kinds of planets in the galaxy, have no solar system analog. And their formation is a mystery. Another difference between these planets and gas giants is that you can't infer from their masses and radii alone what their compositions are. Because they're smaller, you could, for a planet the size of Jupiter, you have to have a whole bunch of hydrogen and helium to make it big enough. For a planet that is 3 times the size of Earth, you could equally well explain it as a very, very dense iron core with a low mass hydrogen envelope, or something that is made mostly of water ice. Those two things produce the exact same mass and radius. And so in the absence of studying the atmospheric composition, we don't know what they're made out of. We would expect from planet formation models that the metallicity of their atmospheres is higher than for giant planets. So this peak here corresponds roughly to the peak in planet radius that I showed on the previous slide. And you can see that they're expected to be metal enriched. Higher up on the y-axis is higher metallicity envelope. And we would also expect a lot of diversity. We don't know exactly the shape of this. The different colors correspond to different properties of the planetesimals. I think planetesimal size. And so the goal is to go out and measure the atmospheric composition of one of these objects and see, does it fall in this range? We don't know. And however, these planets are very challenging to observe because, as you'll remember, the size of the feature is proportional to the radius of the planet. And so if you cut your planet radius in half, that decreases your signal to noise by a factor of 4. And so there's only a handful of small planets that have been accessible for atmospheric studies so far. And they're all listed up here. And I want to talk about one of them in particular. This is GJ1214b, which should be a familiar planet in this crowd. This was discovered by the MIRTH survey led by our own Dave Charbonneau. And I call it everybody's favorite super-Earth because it's the single most feasible planet in this size range. And so this figure is circa 2013 or so about 5 years ago. And everybody and their mother observed the transmission spectrum of this planet. This is just the most precise data that I'm showing here. And it was a mystery. So what was found is that the spectrum was very flat, consistent with a flat line. But there are multiple different ways to get a spectrum like that. One is that you can increase the mean molecular weight of the atmosphere, which will shrink your scale height and make your features smaller. Alternatively, you can put clouds at high altitudes, and that will truncate your spectral features at wherever the cloud altitude is. Yes, I just said that. Okay, so this was really frustrating, and the only way to tell the difference between these two scenarios is to get higher precision data. So this is work that I did as a grad student, where I observed a record number of transits for this planet with Hubble. This was a 15-transit observation. And the goal was to measure a spectrum so precise that even if it had a very high mean molecular weight atmosphere, even if the atmosphere were made entirely out of water, we would still be able to detect spectral features. That's not what happened. We measured a very, very, very flat line. This has been called the most expensive flat line in astronomy. But we know, and it's very informative. Just because we didn't detect anything doesn't mean we didn't learn anything. So I'm comparing our spectrum to a couple of plausible high mean molecular weight models. What we found is that the spectrum is so flat that even an atmosphere made purely out of CO2, which is the heaviest plausible molecule to dominate your atmosphere, we could still rule that out at high confidence. And so our conclusion is that there must be clouds in this planet's atmosphere. So this was a little frustrating because we wanted to know what the atmosphere was made out of. And we found that when we went back and asked for more observing time to look at more planets, the TAC said, they're all going to be cloudy. Why are you doing this? But we kept pushing and pushing along with many others. And over the last couple of years, we built up a sample of these small planets and found that indeed some of them do have very nice visible absorption features from water. And so this is a paper I wrote with Ian Crossfield last summer where we wanted to search for trends to try to figure out which planets have flat spectra and which ones don't. And we identified, based on our sample size of 6, a trend with feature size and equilibrium temperature. And this was the perfect moment to write this paper because when you have a sample size of 6 objects, it's too big to talk about each one individually anymore, and it's small enough where you can identify a very simple trend and have it actually work. So this is our trend, water feature amplitude as a function of planet equilibrium temperature. It's possible that you could also kind of fit this with a step function rather than a line. And we think that this roughly 850 Kelvin marker is an important turning point in cloud and haze formation because below those temperatures, methane becomes your dominant carrier for carbon as opposed to CO2 or CO. And methane is really, really good at making haze. So if you take methane molecules and you irradiate them with UV light, they break up easily and then recombine to form these higher order hydrocarbon hazes. So it's which are seen in abundance in the solar system. We've seen them in Titan. We've even seen them in Pluto. And so it's possible that something similar is going on in the exoplanet atmospheres. But to confirm this, a bigger sample of planets are needed. Ian and I have a large HST program from the last cycle that is looking at 4 new planets that were discovered by K2, all in this general size range. And we'll have many, many more even better targets coming from TESS. Oh, and just so if y'all saw my ITC lunch talk, I got to talk in depth about this planet WASP 107b, which is in this smaller planet mass range. And we see a nice water feature, a number of other things. Point is, we got a new data point to put on our plot. And hey, there it is. which, like, amazing, right? I felt like a theorist. I made a prediction and it actually worked. So we'll see. Now that we have more planets coming, we'll see what happens. But I was very excited about this. Okay. And yes, yeah, here's again from the same paper with Ian, we predicted the number of test targets that would be feasible candidates for these kinds of observations with JWST. And we find that there are dozens and dozens of them, more targets than we can realistically observe. All right, in my last couple of minutes, I want to talk about Earth-like planets. We're all really excited about this. Their atmospheres have barely begun to be probed just because the signals are so small. You're dinged twice in terms of how hard it is. One is because the planet radius is smaller. The other is that we don't expect Earth-sized planets to be able to hang on to a hydrogen-rich envelope. And so if they do have atmospheres at all, they'll probably be these heavier, high mean molecular weight atmospheres that compress your scale height and shrink your features. And very excitingly, just in the last couple of years, we have discovered a whole bunch of nearby transiting planets orbiting very small stars. So 7 of these are from the TRAPPIST system. There's also GJ 1132b and LHS 1140b, which were discovered here, the CFA, as well as Proxima b, which is not transiting, but still exciting, being a habitable zone terrestrial planet around our nearest star. And so the biggest question for me, initially at least, is can these things hold on to their atmospheres or not? In some ways, they're very similar to Earth. They're comparable to Earth in mass. Some of them are comparable to Earth in insolation. But their periods are much shorter because they're orbiting small, cool stars. Their orbital periods are a couple of weeks at most. And this has important ramifications for what their atmospheres might be like. So M dwarfs have long pre-main sequence phases where they're very bright in the UV. This is a figure from a paper I have in prep with a student, George MacDonald, where we're looking at how planet occurrence depends on the lifetime integrated high energy radiation a planet experiences. So this is the lifetime integrated X-ray flux expected as a function of stellar mass. And you can see that for an M0 star over here, you expect about an order of magnitude more X-ray flux in its lifetime than you get for an Earth-like planet. And that could spell bad news for your atmosphere. In addition to these early bright pre-main sequence phases, the stars are often active, they're flaring, there's stellar wind, and the planets are expected to be tidally locked. And that poses its own dangers for the atmosphere. You can have a situation where the atmosphere will collapse on the night side and freeze out, kind of like a snow cone. And that's also bad. So, it's possible that there are ways around this. If you have an ocean that helps transport heat from day side to night side, there's a lot of physics and chemistry that we don't fully understand. So I wouldn't say that terrestrial planets around M dwarfs definitely don't have atmospheres, but there are these challenges. And so we want to observe them as soon as possible to figure out whether these systems are hospitable environments for life or not. So I want to finish up by talking about a paper I wrote with Caroline Morley, who is a Sagan Fellow here at the CFA. And we wanted to say, all right, we've discovered these nearby planets. Now can we actually go out and observe them? What can we learn with JWST? And so Caroline used the solar system as inspiration. She looked at the diversity of atmospheres around small planets. And there's a huge range. You have a very thick 100-bar atmosphere on Venus that's mostly CO2. Earth, at least for now, is fairly clement. Titan is also a nitrogen-dominated atmosphere of about 1 bar. But rather than having a hydrocycle, it has a methane cycle instead. And finally, Mars has lost most of its atmosphere and has a very tenuous envelope made mainly of CO2. And the reason for this diversity is that there's a whole bunch of processes that go into shaping the atmospheric composition of a terrestrial planet. One is the delivery of volatiles by comets, so what came to the planet as it was forming. The interior composition also matters in terms of what material can be outgassed from the planet. The planet mass is important. That controls how the core solidifies and cools, which is related to what materials get outgassed. The atmosphere can erode or escape over time due to interactions with the radiation from the star. And all of these things combine to form a very diverse set of possible outcomes for terrestrial planet atmospheres. So Caroline made a grid of physically motivated plausible atmospheric compositions using the Earth, Titan, and Venus as end case scenarios. And she took the compositions of those atmospheres and broke them into their constituent atoms. So Earth is mostly oxygen and nitrogen. Titan is mostly nitrogen with some hydrogen, some carbon. And Venus is mostly C and O. And then she ran a grid of models with a range of surface pressures for these nearby newly discovered terrestrial planets, so assuming the masses and temperatures of those systems. And then I took those models and I said, okay, if the planet's atmosphere looks like this, what can we do to actually detect it? So I simulated JWST observations with the Pandexo tool that was developed by Natasha Batalha. And I made some ad hoc criteria for what constitutes a detection. And it looks something like this. So this is the example of TRAPPIST-1b, assuming a Venus-like composition with a surface pressure of 1 bar. The different colors correspond to different atmospheric compositions. Earth is blue, Titan is yellow-orange, and Venus is red. And so this top panel corresponds to the emission spectrum as measured by MIRI LRS between 5 and 10 microns. And you can see that with a total of about 10 eclipses, you can start to detect features at high confidence and distinguish these models from each other. So not only is the atmosphere detectable, but different compositions correspond to spectral features from different molecules. So Venusian composition is mostly CO2 features, Earth-like composition is mostly water, and a Titan-like composition is mostly methane. Similarly, for the transmission spectrum I'm showing on the bottom, you can detect it with about 6 transits. This is with the NIRSPEC instrument. And our focus initially was just on detection, but you could see that some of these models would be easily distinguishable from each other, in particular Venus versus Titan. So you may be wondering whether I cherry-picked this example. 9 eclipses, 6 transits sounds very feasible. I did, in fact, cherry-pick. TRAPPIST-1b is a little bit easier just because the temperature of the planet is higher. This is about a 500 Kelvin equilibrium temperature object. If we look at the others, here's a big old table showing how many transits or eclipses are required to make constraints like the ones I just showed you for all of these newly discovered planets. I did 2 cases, and we're learning now that what I've listed as the pessimistic case may be the correct one. There's some uncertainty in particular about the TRAPPIST planets, about what their masses were. And a new paper recently came out with updated TTV measurements that push the masses a little bit higher, closer in line with what you would expect for an Earth-like composition, which makes these measurements a little harder. So focus on the numbers in parentheses. The dashes indicate cases where more than 100 transits or eclipses are required, which I think is unfeasible in terms of observing time. So you can see that it's going to be hard. There are a few cases that are pretty feasible. Like, to give some context, for GJ1214b, we observed 15 transits with Hubble. So this is in the ballpark, for a very important planet. We could totally get that much observing time. If you're pushing to 30, 40, 50, I'm less convinced that that would be a compelling thing to observe. So what does that give us? Well, some of these are looking real good. So GJ 1132b should have a very well characterized atmosphere with just a couple of secondary eclipses. This is top of my list of JWST proposals to write. TRAPPIST-1b is already included in the GTO programs. Transmission in general is a lot harder than emission. And for multiple reasons, just in terms of getting the signal to noise you need, but also in the interpretation. Importantly, these models do not include clouds. So the cloud-free case will give you the largest signal possible. If we didn't detect anything, that could have multiple interpretations. It could mean that the atmosphere has been lost, or it also could mean that there are thick clouds high up in the atmosphere, as we've seen for other planetary systems, and there's no way to tell from transits alone which one of those is the case. So my money is on thermal emission for the hottest planets. I think that that's our best bet in the early cycles of JWST to make inroads on what kinds of compositions are possible for these planets around the lowest mass stars. And we did push a little bit harder because you'll notice that the hotter planets are not the habitable zone planets that we're absolutely most excited about. And so Caroline and I said, okay, what if we really, really push, what is possible for planets in the habitable zone? And what we found is that if you go to the longest wavelength, so this is a color magnitude diagram with MIRI filters. This is the 21 micron filter, and this is the 21 micron to 13 micron color. And we looked at TRAPPIST-1, D, E, and F, which are all in the neighborhood of the habitable zone. And we considered which cases would be detectable with 15 eclipses in total. And what we found is that some cases are detectable at 3 sigma confidence, and some are not. The Titan-based cases tend to be easier because methane is a strong greenhouse gas. And at 21 microns, you get a nice window to the surface. You're actually seeing the hot surface there. And so this is a starting point. I would say it's by no means the be-all and end-all of habitability of planets, of terrestrial planets around M-dwarfs, but it is, I think, what is realistically achievable with JWST and will be an important and a really important data point in starting to rule in or rule out what classes of atmospheres are possible. So just to wrap up, I'll say that I hope I've convinced you that detailed atmospheric characterization is possible with the highest precision measurements. We can learn a lot about the abundances, abundance ratios, climate, cloud properties of planets that are many, many parsecs away. And that JWST is going to be absolutely amazing for these kinds of measurements, but it is not the end of the story, especially if we want to start searching for biosignatures in the atmospheres of Earth-like planets. And for that, we're going to need an even bigger, badder space telescope, or observations from the ELTs on the ground, which are very complementary to this. So I think we're close to the top of the hour here, so I'll wrap up. Thank you again for the honor of giving this lecture, and I'll take your questions.
Talk is open for questions. Good.
Hi. Very impressive talk. I was curious about this WASP 103 something when you had this HST and speecher. If you can show the slide again.
Yeah.
So you were detecting emission from the fundamental band of CO. So there is a 3.0 band of CO, which is the second overtone at 1.61 micron. So were you correlating this?
Yeah, it was included in our model. I think that the opacity is too low in the WIPC3 bandpass, and it would be drowned out by opacity from other species like H- and the H2H2 continuum. Yeah.
So I have a question about the, this is more appropriate to your hot Jupiters, I think.
Yeah.
So when you're tidally locked, right, any warmth at all on the backside has to be advected there by some kind of wind pattern.
Yeah.
Are those adequately modeled? Is
No.
some sort of reasonable expectation of what to expect?
Yeah, so I would say that there's been a lot of work done on this, but there's more to be done. So there are currently 3D models that couple dynamics and radiative transfer self-consistently, but there's a lot of physics that is left out, so like latent heat, condensation of clouds, those kinds of things are not included. So the baseline effect of having wind that moves heat around, that's in there. But it's just a starting point.
Okay. And you probably said this, but is the dark side actually detected at some level of significance, or could it be completely dark, like black?
Yeah, so in this case, for this particular planet, this is as close as we can get to the night side. Actually, I don't have the slide, but we see it in the transmission spectrum, actually. If you don't correct for the night side emission of the planet, it shows up. Yeah.
Thank you. Go ahead.
So, just thinking of tidally locked closing planets, like Mercury is in what, a 3 to 2 or a 2 to 3, like it's not 1 to 1. Is that considered possible for M-dwarf habitable planets, and how would that change the atmospheric modeling?
Yeah, I think so for the really, really low mass stars, planets in the habitable zone have such a fast tidal locking time scale that they're expected to be fully locked. I think there are probably people in this room who know a lot more about this than I do, but for the slightly lower mass M-dwarfs, like an M0, then it starts to become a question as to whether they're fully tidally locked or not, which would totally change the expectations for the atmosphere.
Go ahead.
You presented all those predictions for the JWST, and you haven't talked about the ELTs.
Yeah.
So are those useful for this field? Okay, so they're not useless.
Thank you for asking.
Okay.
Yeah, I had so much space telescope stuff to cover that I didn't have time to do the ground. So the idea with ground-based observations of transiting planets is that if you look at very high spectral resolution, you actually see the planet's Doppler-shifted signal. So you can distinguish the signal from the planet from our own telluric absorption and the stellar spectrum, and you can use that to isolate the features from the planet. And it's possible that if you stack together a lot of observations on an ELT, you could potentially detect something with molecular oxygen around an Earthlike planet.
So, are you and your friends really going to get all this JWST time? Because you need to cover the phase. It was actually designed to be a cosmology.
We don't
Spitzer and Hubble also have apparently cosmology science cases.
I will say that's a cheeky question, but that's not as bad as what Mikhail Guillaume asked me, which was, what are you going to do if JWST explodes on the launch pad? I was like, don't ask that.
That would be too easy. All right, if there are no further questions, let's thank Laura again.